This conference will now be recorded.
Yeah, was waiting for that cue. We are on record. Ahmed, please kick it off. Okay, I guess there's some difficulties and we'll allow him to fix it. Okay, so for the meeting today, I'll kick it off. We had planned four topics to go through, each about 15 minutes. So the first one is updates on Facebook's timing card implementation, and then followed by Aurelia timing card implementation, and then NVIDIA's timing card implementation. Last would be closing remarks from ELPROMA. I see you guys are on. Hi, thank you for joining today. And without further ado, let's go to Facebook's timing card, and I believe Oleg, you will be taking this one.
So let's see if we can do it now. Okay, great. Finally. Okay.
That's good.
So I think you have the view. Okay, so we have, again, before I start digging deep in this, we have already like this discussion that we want to change the name to something more inclusive. So for now, for the time being, we just got Grand Main Clock, so we can keep the GM, and then we'll basically have this discussion about the name in a different time. So starting with this block diagram, we think that this is everything you need to build a Grandmaster. This is basically the general picture. Like you need a GNSS, you need a high stability oscillator, you need a network interface, obviously, and some sort of logic and processing in the middle that can be interpreted with like whatever basically the need is. So and then there are different pathways they can exist or not based on your implementation. That like we try to make, again, this is like a general definition of like what you need to have in order to build a Grandmaster. So the simplified approach is if you just use, let's say, a GPS discipline oscillator, which they're like you can get them again from something very cheap all the way to more like elaborate solutions, which they basically incorporate the GNSS or GPS receiver, providing the PPS signal to basically do this thing called disciplining the oscillator. So you do the disciplining of the rubidium clock or OCXO, TCXO, whatever is available there, while GPS exists. And when GPS is not available, you continue basically your holdover with your clock. So as I said, like such things exist as like off the shelf, and you can just use them. And then you get the via USB, let's say the TOD and the PPS. So the PPS in the simplified approach should go straight to, let's say, to the PPS input of a NIC, like off the shelf NIC that is able to do the external timestamping. And then you can get via USB basically the TOD. So there is already a tool, the TS2PHC, that can basically give you relatively good results for, as I said, like a simplified approach to build a Grandmaster. So this was basically our first take. We did this. Like on the left was like the big mess when we started. Like obviously a lot of these off the shelves. I opened them and I was trying like to see compare different oscillators. Like there's OCXOs like from two different vendors. There's a rubidium clock, and that keyboard actually is on purpose sitting there because it was supposed to keep the airflow for these servers. If you keep open these servers, like you need to cover where top of the CPU, otherwise you will have overheating of the CPU. So then with some like let's say refinement and wiring and everything, it became like this. And then we got like some good results on this. So a more reliable and more elaborate, let's say, solution is, let's say, this approach that we have, like with a timing card. So with a timing card, all this, the GNSS and the, let's say, the high stability oscillator and that logic and everything goes basically on one card, and the card communicates, let's say, via PCI Express to the host. Why? Because in this approach, we thought that we put basically a PHC, the physical hardware clock, on the FPGA, and it gets advertised basically to the host as just like another PHC, like an ordinary NIC, but just PHC. And all the synchronization, the synchronization, the adding basically the TOD, everything happens basically on this FPGA, on this card. And then from your end and the host, you can use just a simple tool like, let's say, PHC to sys, which is a good copier for PHCs. And you copy this PHC into your PHC and you can continue. And you can also like approach it with different things. So we started like the development of this board, and the work is definitely work in progress. So this is like the first, I would say, 3D model of like what we got like of the design. So we have basically the, as you see, like it's a PCIe form factor. You have a GNSS receiver, or you can put more, like you can put 2 for increasing reliability. The FPGA, we decided like to go with a swappable module, so you can, let's say, go with different vendors, go with different specs, performance, or whatever. And then we added like SMA connectors and also SMB connectors on the board if you want to keep all the wirings inside the case for 10 megahertz and PPS, input and output. And then we added also a backup power controller. Let's say you want to, instead of like keeping all the hosts up or something, you can have something just keeps the MAC. By MAC, I mean miniaturized atomic clock. Or you can swap it with an OCX or something. Keep that one up for like some power interrupt. So the clock and the TOD basically keeps staying up. And again, we chose this form factor, this footprint, to make it easily swappable between different options depending on the need, like either OCXO or the MAC. And then we also added some dedicated TDCs, like time to digital converters, to again for various applications, VCO, PLL, and this microcontroller controlled crystal oscillators, like these smart oscillators basically. And then we added also some environmental sensors and like even an RTC to again for different applications if someone needs, like this board can be versatile enough. So as I said, this board is completely hardware and software open source, and we welcome anyone to basically derive their own interpretation and changes or whatever they want to do on it. Fully compatible with TS to PHC and PHC to sys, so you can even do external timestamping with this. And as I said, like the PHC will get advertised on the device tree like an ordinary NIC. And the versatility, as I said, is here. You can change it for whatever you want. If there is nothing else, Dotan, we can hand it to ELPROMA.
Sure. Thomas, will you be presenting?
Yeah, sure. Can I get the access to screen, please?
Yes, you just got it. Thank you, Dotan. NVIDIA showing into Thomas, ELPROMA.
All right, so good evening, good afternoon, good morning to everybody. So do you see the screens now? Do you see presentation now? No.
No.
Okay, well, better?
Yeah, we got it.
It was waiting for the
Hallelujah.
Okay, let's go
11:45. Go ahead.
All right.
Perfect timing.
Okay, we like to refer to several previous meetings, including ITFS and also the one we've seen on the LinkedIn and YouTube. So I will quickly make a short introduction, and I will give a voice to colleague, to Janusz, who will give detailed remarks. So the first of all, I want to come with the very good news that we can release open source a lot of GNSS receivers which are the resolution T compatible. That's the standard you have chosen. We have the U-blocks on the board, including Neo, LIA, ZIT, which is a double frequency. But we also recommend some new receivers from the Japanese company Furuno. Especially, we want to highlight that this receiver is introducing to market a new multipath mitigation technology that is really resistant for reflecting signals. Also, I think the members of the family who wants to make their deployments globally, including some East European regions, India, they might be interested in Asia manufacturer like Skytrack or CB-Top. And we have placed the one receiver made in Russia from the company NVS, which currently is in a production for many years, but it seems their development has stopped. So, okay, while we are showing all those receivers, there were several questions during the meeting regarding security. So I want to highlight a very important thing that is mostly forgotten, that time is born inside the receiver. So the receiver is receiving some telemetry data from the satellite system, but currently the UTC or atomic timescale is born inside the receiver. And that means that the accuracy and the stability very much dependent on the receiver. We have chosen only the best experience we have in the previous decades. So we will release those boards, open hardware and open software, whatever. What kind of problems you can expect dealing with the receivers? Well, the most frequent one is a leap second support, which is still, even the PTP is based on the atomic time scale. It seems to be quite a problem. Don't forget that if you follow the dependence on the other than GPS satellite systems, like for example Russian GLONASS, the important thing to highlight is that the GLONASS basis on the continuous time scale, which means this is by nature the UTC, and the recalculation to the atomic time scale will require some arithmetical transformation. We know a lot of examples where the receivers behaves unstable, and what is interesting, the instability of the receivers frequently is not tightly related with the specific date of adding or subtracting leap second. The very famous manufacturer of the receivers in the previous decades, they noted some firmware problems that occurs many months before leap second and many months after leap second support. There are also other kinds of the problems that are related with the receivers. The most dangerous one are like the one noted on the 26th of January 2016, where the GPS SBM-23 satellite vehicle has introduced 13.5 microsecond error to the system. So those are the things that you should keep on in your head when you are considering stable solution. So I hope this slide can keep your memory on that. So going back to the free gifts we want to offer, the module on the left side, this is a development board. It's designed by ELPROMA team, so you can easily and quickly assemble any of the boards, and you can test it, using USB or RS-232 interfacing, including PPS. Also, I want to refer very shortly to some questions we met during the ITFS meeting. They were regarding jamming and spoofing. More of the receivers you see on the screen, they support kind of the error flag or alarm message indicating there is a jamming or spoofing attack. So the board can quickly be switched to the holdover operation, and it is definitely recommended to do so. But still, the solution the TAP project is designing is aware to use some active filtering of jamming and spoofing. You can see the example of such very miniature filter on the bottom of the page. This kind of the filters are requiring double antenna system, because all the detection of the false signal bases on many comparisons of the strength of the angles of the signal that are received by the receivers. So these are very short news from my side, and I am giving voice to a colleague of mine, Janusz, who will give you more details, information regarding.
Thomas,
Yeah?
I have a question regarding the antenna. We definitely understand this is something that we challenge ourselves. We definitely understand the challenge when we go to telco market and you have like zillions of nodes and sites that you need to be deployed, but we are talking about data centers. Usually those POPs are very limited and very carefully selected in location. Is it fair to assume that we can liberate ourselves from this trouble? We will have an open sky access on top of our roof and that's it?
I don't know. I mean, you know, these days everyone is quite afraid for the cyber attacks. There are some definition of time synchronization attack for the distributed smart grids, for example. You know, they also have the same properties as data centers. So I think we can expect kind of the cyber attacks also to data centers. And that is what some first cases are unknown, but they are not really a good case study available on the internet to learn about. But we know this is going to happen.
So when you say cyber attack, you mean jamming and spoofing? I wouldn't consider that.
Jamming and spoofing, but also, you know, having flexibility on all those receivers I am presenting is quite important, because to ensure the time domain operation and frequency domain operation on a large scale of the country size, very much dependent on the firmware revision numbers and type of the chips that you are going to use. It's not as simple as it seems to be.
I agree with you. Jamming and spoofing are important for data centers for sure.
Yeah, definitely. Okay, let Janusz explain.
Nice.
Oh my goodness.
Move somewhere. Okay.
He needs to move some pictures away.
Maybe this.
Okay.
Okay. Let's see. Now. Okay. Now there is a difference between synchronization your Grandmaster card and network card, and in case of synchronization over PCI Express PTM, you can do something like cross-tie sampling, and this can allow you to average errors and eliminate problem because you have 8 nanoseconds trigger and some capture resolution. And also PTM allows you to compensate cable delay, so you don't need to do cable calibration in case of PPS cable. Now, in previous presentation, you show PLL inside FPGA. Such PLL is more noisy than external one. Another thing, you connected directly 10 megahertz output to your local clock, and it seems it is not controlled, not tuned, so it is rather free run. So you cannot output 10 megahertz when you are using 10 megahertz input. And another thing, you change frequency using PTP hardware clock counter. This has some disadvantages like sawtooth effect, and you have a bigger jitter on 1 PPS input on capture. Here's an example of the jitter, and also sawtooth effect. And one thing more, on the picture there is no filter to implement the second order PLL. So the question is in the picture, on the picture, how you are going to implement synchronization, exactly synchronization. And another thing, here is example of frequency adjustment when you can achieve fractional tuning using some patterns like on the slide. Okay, better thing it would be tuning using digital PLL or directly tuning your local oscillator if it's digital, so you can control it digitally or over DAC. And here's a difference. In case of 10 megahertz input, you can divide the frequency and capture, for example, as 1 PPS or something more frequent, and then monitor and also synchronize to the signals because you have quite stable oscillator. Okay. And there is a question: what is goal for a 10 megahertz output for you? Because it depends how to implement the board is the best. And another question is for 10 megahertz input. What is your clock reference? Is it a reference like a session clock with a frequency offset, or it is corrected? Frequency offset is corrected nearly zero, like from EPMPC.
So I can quickly refer to that. Like the 10 megahertz input is basically another option if someone wants to use, let's say, again, this is like we're trying to build something that everyone can use, like a wide variety. And then the 10 megahertz output was more for measurement. And let's say in case of, let's say you have another application that you want to use this card to synchronize another card, then you can use basically this one as an output to daisy chain, like let's say various things. It's just like another way to do things. For example, I have the external timestamping here that you can use this for other applications as well, because it's not only data centers. Like we're trying to make this as versatile as possible. Like we have a VCO PLL on this that can get, like, essentially you can implement this or like assist an implementation with White Rabbit on this. So again,
yeah, we definitely think more general on your
exactly.
idea.
It's a general. Let's go ahead. Sorry.
Okay.
So that's the, if you can
I
take
think
one.
also we are not, I mean, 8 nanosecond time error is not a goal for a grandmaster on a data center. We care more about stability and holdover.
Yes.
I think we should mention, Ahmed, maybe what is our goal in terms of time absolute error, or at least in general, let's
Yeah,
take.
it's quick because we don't want to take from their time. I want ELPROMA to finish as well. Yeah, let's go ahead and we can.
Okay, shall we continue then?
Yes, please.
Yeah, go ahead.
Okay.
Last 2 minutes.
But good resolution is important if you want to quick synchronization, because you can observe your source in much shorter period and synchronize to it. Here is an example when resolution causes you don't see much smaller frequency offset before 400 seconds. And in case of the board, you can also consider to use super LCD as it's more stable for temperature but Holtover is much better with Ruby oscillator. This slide is not actual after your today presentation, as you included temperature sensors. Well, and here is it is better to use to connect one PPS directly to a PGA also, not only multiplexing the signals, because then you can monitor time error to the potential time source before switching on, and also this could allow you to implement EPRTC. Sure. And there is exactly the same thing with 10 MHz input. You can connect directly to FPGA, and as I showed before, you can divide the clock and measure time error, and then observe and synchronize to the external clock on the correct frequency offset. One word about another your presentation. Of course, when you have two sites and one site has no GNSS, SyncE allows you to reduce noise on site A in this case. So the sites will be better synchronized. And another things why we talk about EPRTC, when GNSS failed, you have jamming or spoofing, and there is no link between sites as here between A and B, but other communication is available. The sites can be still well synchronized, and there will be no time islands. Thank you.
Okay, and I want to end. I start with some timescale information, and I want to end it with the information that, for example, if you synchronize yourself on the node A to the GPS and node B to the GLONASS, you will note it by nature of the timescale recalculation offset something like 30-40 nanoseconds, because that's the natural offset between the Russian timescale and the US naval timescale. Okay, thank you very much.
US is ahead or Russia is ahead?
Sorry?
Who is ahead? Who is more advanced? No, I'm kidding.
In time.
In time.
Okay, thank you very much, ELPROMA.
Thank you.
We've seen today very different implementations. Thanks everybody for sharing, and let's let these things sync and offer a chance to everyone to collaborate offline with any questions or follow-ups.
Yes, thank you, ELPROMA, for your comments. We will address them. Thank you.
Thank you, everyone.
Thank you, guys.
Goodbye.
Goodbye. Bye.
Thank you.